Okay. So the screen is visible to all?
Yes, ma'am, visible. Yes.
Okay, okay, fine. So today is the ninth week of tutorials on fundamentals of power electronics. Today our topic of discussion will be design of inductors and design of transformers. Mainly, we will mainly focus on high frequency transformer design. Okay. So first of all, what is the need to learn all these things? Because when we were studying the DC-DC converters, the non-isolated DC-DC converters as well as isolated DC-DC converters, so we saw that there were some magnetic components present in the circuit. For example, in buck converter or boost converter or in buck boost converter, you studied that there was one filter inductor, right? So that inductor value also we calculated via different numerical problems, and we know how to calculate the inductor value. And if we take the isolated converters, forward converter or flyback converter, there also we saw that there was inductors as well as transformers, because they are isolated, so there will be one high frequency transformer. So it is essential for us to know how to design the inductor and the transformer, right? So today we will discuss what is the procedure and what are the different steps to design inductor and design transformer. Okay, let's see. Before going to the design process, let's just talk a bit about the basics of magnetics. Okay, so if you take any magnetic component, say it inductor or transformer, there are mainly two parts of a magnetic component. One is called the core and the other part is called the winding. So core is basically a ferromagnetic material which is able to so the flux basically flows through the circulates through the core, and there is the winding part which is nothing but a wire, copper wire, some conductive made of some conductive metal. So this is kind of the structure. This is a very generic structure. So suppose this is the core. This could be of there. Later we will discuss core can be of different shapes and sizes. So for now, just suppose that there is this rectangular cross section, and the core is this shape, and over that we have wound some wire. So this becomes the winding. And if we give some voltage here, that we call the excitation, if we give some voltage, some current flows through the winding. Suppose the current direction is as shown here, so it enters here and then it goes like this and comes out via this wire again, right? So if there is a core and around that you have wound some wire, so some flux will get generated if the current is varying in nature. Okay. So some flux will get generated and we will get some, if there is some d phi by dt, that is the rate of change of flux, then some voltage will induce, right? We know from Faraday's law of induction that if there is rate of change of flux, then the induced voltage is n times d phi by dt, where n is the number of turns. Okay. So suppose we have this kind of a code. This is the code, and here we have shown the current is going inside in this direction and it is coming out from this side. So if you see the cross section, so this cross indicates that current is going inside, and this dot indicates that current is coming out of this plane. right? So if you have wound the wire like this, there will be some flux that will get generated and that will circulate in the core. Okay. So there are some terms that you need to know. And there is one important law which is called the Ampere's law. I think we all have studied all this in our like class 2 and all this 11 and 12, mainly in 12 maybe. But anyway, I will discuss it. So this MMF, what is MMF? MMF is magnetomotive force. So MMF is basically the what Ampere's law states. It states that MMF is the integral of H times dl in a closed path. So this circle indicates that it is a closed path. Okay. That is equal to MMF, and MMF is N times I. So N is the number of turns, I is the current flowing through the winding. So H integral H dl is Ni. What is H? H is the magnetic field strength and dl is the uh, dl is basically a very small length, infinitesimal length, and if we integrate it, we get the magnetic path length, the mean magnetic path length. So H multiplied by Lm is Ni. So magnetic field strength is Ni by Lm. So this is a very important law for magnetics. Okay, this is a very fundamental law, and we will need this while discussing the design process. Okay, we will need this equation. Another very basic law is Faraday's law that we already know. The induced EMF is N d phi by dt, where d phi by dt is the rate of change of flux, N is the number of turns. So, if we want to find out what is the flux, then we can integrate this. And flux is basically, so B is equal to phi by AC. What is B? B is the flux density and AC is the cross-sectional area of the core. So we were discussing, so this will be the cross-sectional area. The area of this portion is the cross-sectional area. So if you divide the flux by the cross-sectional area, you get the magnetic flux density. So many a times, most of the times, we actually use B in our equations rather than flux. If you will see in when we will discuss the design process that B is very important in our discussion, and most of the time we shall use B in our equations rather than flux. Okay, so flux density we will use in our equations, and this curve here that I have shown, this is called a BH curve. Okay, this is called a BH curve. So B is the flux density, H is the field strength, and this is, if you see this portion is kind of linear. This portion is linear, and after that there is a knee, and then this curve more or less becomes flat. It is not completely flat, but it is, the slope becomes very low compared to this portion. So when we will design the inductors or transformers, we shall always try to stay in the linear region. If it goes in the saturation region, then we will not be able to operate our circuit properly, because here if you see, so so if you just see this equation, you can see that H is basically, H we can derive from the current. Whatever current we are injecting, from there we can have an idea of H. N for a particular inductor, N is constant, number of turn is constant, and Lm is also constant for a particular core. So the variable is current. So if we know the current, we can have an idea of H. So here, even if you increase the current, so the mmf increases, but the change in B is very small. If you see this portion, for this current B is this much, and if you increase the current here also, the B is almost same. There is very insignificant change. But here if you see, as the slope is high here, so here if you change the current, your B will also change significantly. So this region is called the saturation region, and we get the saturation region in the positive, uh, in this region also and in this region also. Okay, in the first quadrant also, in the third quadrant also. So actually, in practically, if a transformer or an inductor goes into saturation, then it will draw huge current. So it will no longer behave as an inductor or a transformer. So it will draw huge current and it will get heated up and your circuit will not function properly. So we will restrict our design in this portion, in the linear portion. And one more important thing is this slope of this curve. This is called mu, the permeability of the core material. This is called the permeability. I shall write it down. So this is mu is called the permeability of the core material. So this is the property of the core material. If you change the core material, the mu will also change. The mu value will also change. Okay. So this is mu. This is mu. And it varies with as you change the core material, the mu value varies. Yeah. So another important point is, so if you see, suppose you started magnetizing the core like this. So you have some current, you have some magnetomotive force, mmf. So the core starts magnetizing. So it is magnetizing here and it reaches here. And then if you again decrease the mmf, you will see the curve will not come back like this. So it started from 0 here. It went on increasing. But when you will again decrease the mmf, so it will not change in this way. It will change like this. So here, if you see in the y-axis, so now your mmf is 0. There is no mmf, but still there is some B that is remaining. Okay. So you will have to provide some negative H to make B 0. Okay. And again in this third quadrant, it goes like this. And again, here again there is some B. And if you apply some positive mmf, it becomes 0 and it goes like this. So this curve is called the hysteresis curve. And the area under this hysteresis curve, this is called the area under the hysteresis curve indicates the loss, hysteresis loss. In the core also, there is some loss. Okay. In any magnetic material, there is some copper loss or which is caused due to the conduction loss in the material, because if you are winding, then there will be some resistance associated with the windings and some power is dissipated there. That is called the conduction loss. And there is this loss which is incurred in the core. This is called the hysteresis loss, and there is another loss that is called the eddy current loss. So eddy current loss and hysteresis loss, these two losses occur in the core. And higher this area, higher will be the core loss. right? So yeah, so we can simplify this curve. So in this knee region, we can make this piecewise curve. So here it is completely linear and then it becomes flat. Although actually the curve is not like this, but we can approximately use this piecewise curve. So linear and then flat. Okay. This is B set, the saturation flux density, and this is minus B set. Okay. And when we will design it, we will restrict the maximum flux density till this point, suppose. So we will have some margin from the saturation flux density and we will restrict our design within this region. This is the safe operating region.
Excuse me, ma'am. Hello.
And there are some other things as well. So B is equal to mu H that we already saw. And B is phi by AC, the cross-sectional area of the core, is equal to mu times H is Ni by Lm that we already saw. So this is equal to mu times mmf by Lm. Okay, so phi is what? Mu AC by Lm times mmf. Okay, so this quantity is called the permeance. This mu AC by Lm, this quantity is called permeance. And the reciprocal of permeance is called reluctance. Okay. So phi is permeance times mmf, or you can also say phi is mmf by reluctance. Okay. And here what is shown is that suppose your curve is like this, but for an inductor, uh, so the energy stored in the inductor is half L I square. Suppose you want to use the same code, but you want to store more energy. So you want to store more energy. But here, if you reach this point, so the core is already saturated. So beyond this point, you can't increase the current. So what we do is we try to make the curve like this. Instead of this slope, we reduce the slope and we make the curve like this. So if now you see, you can increase the current like this till this point. Because now the slope has reduced, so you can increase the current. So half Li square will, so it can store more energy because now you can go up to more current here. So we will see how this is done. We can introduce some air gap, okay, or you can use some core materials whose mu is lesser, okay. But this way you can store more energy in the inductor. Fine. Here some more equations are there. So we already saw that phi is equal to permeance times mmf. And if you multiply n here, n d phi by dt, it becomes permeance n square into di by dt. Okay. So this n d phi by dt, this is the induced EMF according to Faraday's law. And this portion, so we know that the voltage induced across the inductor is L di by dt, right? So di by dt is already there. So this quantity we can say this is the inductance. So this is L di by dt. So what we got from here, we got that inductance is permeance times n square. What is permeance? The permeance is mu 0 mu r AC n square by Ln. What is mu 0? What is mu r? So here we have shown mu, right? So this mu is multiplication of mu naught and mu r. What is mu naught? Mu naught is the permeability of free space, which is 4 pi into 10 power minus 7 Henry per meter. And mu r, this is called the relative permeability of the core material. So if you are not using any core material, it is just a air core inductor, so then your permeability will be mu naught. But if you are using a particular core ferrite material, or suppose any uh, powdered core or something, any core ferromagnetic material, so you will have to multiply mu r, which is the relative permeability. Okay. So now if you see, we have expressed the inductance uh, in terms of the dimensions of the core, right? So these are all, we can get all this information from the core data sheet. So mu zero you already know, mu r you will get from the data sheet. AC you will get again AC, the cross section area of the core you will get from the data sheet. LM is the magnetic path length. Again, this will also be provided in the data sheet. And N square you will know, the number of turns will be known to you. So all, if you know all of this, you can design your L, right? So we have expressed the inductance in terms of these quantities. And EL, this is the energy stored in the inductor. We can represent this as half AC B into MMF. So we can represent the energy stored in the inductor like this. So you can rearrange these equations. You can use all these equations that we saw, this one, and then all these equations. And you can see that the energy stored in the inductor is this. Okay. So we will use all these equations when we will design the inductor. Yeah, so what I was saying, that if we want to increase the energy stored in the inductor, we don't want to change the core. We want to use the same core, but we don't want it to saturate. Then we will have to change the mu. How we will change the mu? We will have to change the slope of this curve. We will have to reduce it. So if we reduce it, then we can go up to higher current and it will not saturate up to this point. So we can go up to this point. So here the current is obviously more than this point, right? So that's how we can use the same core to store more energy.
And how to change mu value, ma'am, in that case? You
Yeah,
are
so
telling
there
me.
are different. So
Yeah, yeah.
usually for DC-DC converters, if you are suppose using a ferrite material, so you will have to introduce some air gap. If you introduce some air gap, then essentially what you are doing, along with the core material there is some air gap. And for air, you know that the mu is very less, right? For air the mu is mu zero basically. There is no mu r. For air mu r is 1, the relative permeability is 1. So that then the effective mu reduces and the slope reduces. Okay, we will
Okay,
see
okay.
that. I will explain the design steps there, we will see.
Where can we get core, ma'am? Ferrite core? Any company,
Yeah,
any
yeah,
idea?
there are many manufacturers of
Ma'am,
so there is
we are working on wireless power transfer,
okay,
and
okay.
we are trying to get the ferrite material. We are unable to get it. So,
So
if you know
there is
any,
yeah, there is Cosmoferrite. Cosmoferrite is one manufacturer. They provide I think they provide powdered core as well as ferrite cores. Then there is magnetics is there. So Cosmoferrite you can search. They have their catalog. You can search in the
okay,
internet. You will see.
so, okay, ma'am.
Uh, so yeah. So these are there. This is a list of different types of core materials. Okay. So first is ferrite. So this material is basically used in high frequency transformers and also for making inductors, high frequency inductors also. So the mu value of ferrite is very high. The relative permeability, it is in the order of some 2000 to 2500 or 1500 like this. So this is ferrite material. Okay. And its Bmax is, so there is a limit for every material beyond which it will go in saturation. So its B saturation is some 1.5 Tesla. Okay. 1 point, sorry. Its B saturation is low basically, not high. Uh, so its B saturation is, I think, 0.3 Tesla like that. 0.3. So usually we restrict the Bmax value while designing to 0.25 or 0.2 like that. Okay. For this powdered core, their relative permeability is lesser than ferrite, but their Bmax is higher than ferrite. So their Bmax is 1.5 Tesla. Okay. 1.5 Tesla. So we can restrict our design value up to 1.4 Tesla or 1.3 Tesla like that. Another one, I think you have heard of this one, CRGO, cold rolled grain oriented silicon steel. So this is used in low frequency transformers. If you have seen any power transformer in any power generation power in any power plant or something you have visited, then you will see very big power transformers which are 50 hertz or 60 hertz transformers. So that's why they are called low frequency transformers. So there this CRGO is used, and there you will see laminations to reduce the eddy current loss. Some laminations are used instead of continuous material like continuous sheets. So they have some 1.2 Tesla Bmax. Okay. So they are mainly used for low frequency transformers, CRGO. And there is another one, CRNGO. It is cold rolled non-grain oriented silicon steel. So this is a low quality core material compared to CRGO, and they are used in for machines, for induction machine or some other electrical machines. So these are the different types of core materials. So based on our application, we can choose which core material will be suitable for us, and we can choose. So mainly for high frequency applications, ferrite core and powdered core, these two are used. Okay, so where you will have the requirement of high flux density, there we will have to use powdered core. And where you will need like higher permeability, but your Bmax can be lower, there we will use ferrite core. And if we use ferrite core, and then we will have to introduce some air gap so that it doesn't saturate. Okay, so we usually introduce some air gap in the core.
When we introduce air gap, what will happen, ma'am?
So then your mu will reduce.
Okay.
So your mu will reduce, and then there will be the risk of saturation that only I showed here. That here in this current only there is a risk of saturation, but if you introduce an air gap, your slope reduces, your mu reduces, and this slope also reduces. So now you can go to higher current and it will not get saturated. Okay, so that is
Okay.
the point of introducing air gap.
So the energy will be stored in the air gap.
Yeah, right.
Okay.
So now we can we shall start the steps of designing the inductor. So this is this figure. This is the figure of a EE core. So why E? Because this is the shape of an E, alphabet E. So this is one E and this is another E. So this whole assembly is called an EE core. Okay. There are different types of cores. If you tell I can share you the link of any catalog or something, you will get in internet various data sheets. But yeah, so there can be E core, there are ETD cores, there are toroidal cores, there are pot cores. So various types of cores are available. And this area here, so there will be some gap here. So this area and this area, this is called the window area. Okay, this is called the window area where you will basically do the winding. So the winding will be around the core. So to accommodate the windings, this free space is there. Okay. So and cross section area we already discussed. So there will be one core cross sectional area, and this is called the window area. And area product is basically the multiplication of the core cross section area and the window area. And it is meter to the power 4. This is called the area product. So this is an important parameter for designing the inductor. Okay, designing inductor as well as transformer. So area product. If you open any core data sheet, so you will find this parameter in the data sheet, area product. There is another factor which is called the window utilization factor, KW. So as you wind the wire in this here, so you understand that you can't utilize this entire area. First of all, around the core there will be one former. Okay, so the former will take some space. Former is nothing but some kind of like non-ferromagnetic material that we. So this has the same shape as the core, and we place it over the core, and over that former we wind the we do the winding instead of directly to the core. Okay, so this is kind of a cover, you can say, some protective cover over this core. So around that former we do the winding. So that's why it takes some space. And again, these are circular cross-sectional wires. So then you can assume, you can understand that there will be some gap because they are circular wires. So when you will wind it, some gaps will be there. You can't avoid that because here you can't use this space. Here again there will be some gap. So that's why we can't use the entire window area. So that's why this factor is introduced, window utilization factor, and this value is less than 1. It varies mostly between zero point 0.4 to zero point 0.6 like that. Okay. And whatever number of turn you choose, and if this is your wire cross sectional area, so if this is one wire, this is the wire cross sectional area, right? This one circular, this area. So n times AW should be at least equal to KW AW. Most of the time it is basically it should be greater than KW AW should be greater than n into the wire cross sectional area. Why? This means that you can accommodate your entire winding in the window. If this quantity, the right hand side quantity is greater than KW AW, that signifies that you can't accommodate the winding in this window. So you can't accommodate it. Okay. So this condition should be fulfilled when you will design the inductor, okay, or the transformer. So AW is the, I already told, this is the wire cross sectional area, and this is what IRMS by J, where IRMS this is your RMS current, and J is the current density. Okay, J is the current density. Fine. So yeah. And there is another factor called the crest factor, Kc, which is I max by I RMS. This is the peak current, maximum current, and this is the RMS current. The ratio of the maximum current to the RMS current is called the crest factor. So KWAW is what? NIM by KCJ. Where does this comes from? From this equation. So this is NIRMS by J, and IRMS we are replacing with this. So IRMS is nothing but IM by Kc. So if we replace this, we get the maximum value of current as this. And here again we are using Faraday's law. So E is equal to L di by dt equal to N d phi by dt. So this is phi is what? B into AC, right? B times AC. So that we saw your flux density is phi by AC. So this is phi by AC. So that only we are replacing, this becomes dB by dt. So LIM, so if you just remove this differential from both the sides, so this becomes LIM equal to NAC into BM, where is it? This is the peak flux density, this is the maximum current. So this is another equation. So these are small equations. You don't need to remember, you just understand it, and eventually you don't have to memorize it. Okay, you will understand. This is the energy stored in an inductor, half L Im square. This is the maximum energy. Okay, so the maximum energy that the inductor can store is half Lm Im square, where Im is the maximum current. So if you just separate these two Ims, Im and Im here, so we already saw Lim is in ACBM and Im is this expression. You just replace it and you will get an expression for area product. Okay, so the area product is 2EL by KW KC JBM. This is the area product. That's how you can get the area product value. Now, the summary of the steps, how to design an inductor. Okay, this is the summary. So the first step is, obviously you will find the inductor value. Okay, we already saw how to find the inductor value. For the non-isolated converters, we solved the numericals, how we can find the value of inductor. If we have a particular specification that we want to restrict the current ripple within some percentage of the average current, then we can find out the value of L. And if we have the value of L, then we will have to calculate the area product. So we have the value of L. We know what is the maximum current that will flow through the L. So we know EL, right? EL we can find out from this equation. EL equal to half L Im square. From this equation, we will get the value of EL. So 2EL KW, we can take any value from 0.4 to 0.6. And KC, we will know. J, we will take 3 into 10 power 6 ampere per meter square. This is a standard value that we take. And BM is the peak flux density. So from this, we can find out the area product. And if you have if you have found the area product, then you can refer to the code datasheet available and you can choose the appropriate code for your inductor. Okay. From the datasheet, you can choose what is the area product. Then what is the next step? The third step will be to calculate the permeance. Okay. So see here they have introduced one air gap. So if you don't want to saturate your code, usually we introduce a small air gap, LG. And will you find this air gap length? How do you know what will be the air gap length? So we know reluctance is the reciprocal of permeance. So that is Lm mu AC plus Lg by mu naught AC. So if you introduce an air gap, the expression of reluctance changes and it becomes Lg. This extra term comes from the air gap. Okay. So the permeance is like this. If you just divide mu r like this, so this quantity is very small, because usually if you take ferrite core or any ferromagnetic material, so mu r is much less than 1. Okay, it is very large, and Lm is maybe some millimeter. So this quantity is very small, and so therefore we can neglect this term, and the approximate equation will be mu naught AC by Lg. Okay, this will be the permeance. This will be the permeance. Okay. And if you don't have any air gap, then there is this factor L that is given in the data sheet, whose unit is nanohenry per turn square. So from there you can find out the number of turns directly. So you already know the inductance value that you require. You know the permeance. So you can find out what will be the number of turns. Okay. Otherwise, if you have air gap, then you can find out the permeance like this. And then step 4 is the winding. We have already selected the core. Now you will have to select the wire with which you will wind the inductor. So there is a list that is called the wire thickness wire gauge. So your required wire cross sectional area you can find out from IRMS by J. So you will have to refer to that list, and from there you will have to choose one wire, okay, which satisfies, so that AW should be your greater than AW calculated. You will choose a wire whose cross section is greater than the calculated cross section. Fine. And then you will have to see whether it satisfies this criteria, that KW is greater than N times AW. If this criteria is not satisfied, then again you will have to choose the next where whose cross sectional area is even more, and again you will have to see if this is satisfied. And this is an iterative process. You will have to continue doing this exercise until this condition is satisfied. Once it is satisfied, then you can choose that particular where, and now finally you can make your inductor with the selected core and with this wire having a cross sectional area of this value. Okay, so these are all the steps. So step 1, find the inductor value L from volt second relation. Then you will have to find the area product. Then you will have to choose the core whose area product is greater than this calculated area product. Then you will have to calculate the permeance, and your number of turns will be root over L by permeance. So this will give you the number of turns, and then finally you will have to choose the where, and you will have to see whether this condition is getting satisfied. If it is getting satisfied, then fine. Then you can proceed to make the inductor. Okay. Yeah. So this entire process has been explained in the lecture. You can refer to it as well. So this process has been explained elaborately. And now we will go to the transformer design part, but I will not go into that very detail. explanation because it is already available in the lecture. I will just tell a little bit about it and then we will proceed to solve the numericals. Uh, yeah, so the basic difference is between the inductor and the transformer is inductor is the energy storing device, energy storing component. So inductor can store magnetic energy and for some time and then it can dissipate it. Okay. But transformer doesn't store energy. It just transfers the power. So it we excite the transformer. So there is some voltage is induced and therefore the flux is generated. The flux couples the primary winding and the secondary winding. And then in the secondary winding, we have some load connected. So the power gets transferred from electric field to magnetic field and again from magnetic field to electric field. Okay. So this is transformed. So here we don't need to change the slope like this as we did for inductor. We were introducing some air gap, but here it is not required because it doesn't have to store energy. So the lesser the magnetization current, the more the better. Okay. For an ideal transformer, the magnetization current is zero. But practically there is some finite amount of magnetization current, and if you the lesser the magnetization current will be, the the performance of the transformer will be better. Okay, so we need to restrict this magnetization current to a very low value. So here you have to make this slope high so that this current is very low. You require very low magnetization current to go to your required Bmax. Okay, you will have to choose the this slope accordingly. The mu value have to be high for that. Is it understood what is the difference between transformer and inductor? So here we need reduced slope because we want to store more and more energy, but here we need to restrict the magnetization current to a very low value. So here we need very high slope. That means that we need high mu. Okay. So yeah. So suppose this is the transformer winding. Okay. So again we need Faraday's law. So this is primary winding. So NP into d phi by dt. This is EP, the voltage induced across the primary winding. So if you want to, so you can write like this EP dt equal to NP d phi and you integrate it. So this is from 0 to Ts by 2 and this is from 0 to delta V. Okay. So suppose you have a sinusoidal excitation the induced voltage is sinusoidal. In the half cycle, the average of this sinusoidal portion you will have to take, which represents EP average. So this gives you the number of turns in the primary winding. Okay. So one of you were asking yesterday, I think in the last class, that how can we use a transformer in the DC-DC converter because transformer can't take DC, right? So that is what is important is you will have to maintain the volt second balance. It doesn't matter what is the shape of the voltage that you are giving here across this winding. But the important thing is you will have to maintain the volt second balance. If volt second balance is happening, then there is no problem. The voltage can be square wave, the voltage can be sinusoidal, the voltage shape can be any random value, but volt second balance has to be maintained. That means that the average voltage across the winding in a complete cycle should be zero. So the average volt, there should be no average voltage across this winding. As long as this is maintained, we can apply any shape of voltage or any magnitude here. Any magnitude means obviously there will be some restrictions based on the other parameters, but it can be of any shape. It can be square also. Okay. It can be square also. So there is no problem. So this is how we can calculate the primary number of turns. Similarly, we can calculate the secondary number of turns in the same manner. So here it will be ES, it will be NS and d phi by dt. So here you here you understand the d phi by dt is same because the same flux. So there is this core, and this is basically the primary and secondary. These two windings are coupled by this core, right? So some flux flows. So okay. So this is the flux phi in the core. So in the secondary also we can write the equation ES is NS, only difference is in the number of turns. So NS d phi by dt. Okay. So actually, if you take the practical case, there is some leakage. So the entire flux is not the flux that is linking the primary. The exact same amount of flux doesn't link the secondary because there is some leakage through through in the air. There will be some leakage. So that flux, the effective flux will be somewhat lesser. But here we can ignore that. We are assuming that the flux is getting linked, the primary and secondary it is same. Okay, so from this equation we can get the secondary number of turns, and here this window utilization factor times this window area is NP AWP plus NS AWS, because there are two windings. In the inductor there was only one winding, but here we have the primary winding and the secondary winding. So the summation of NP AWP and the NS AWS, this should be lesser than KW AW. Okay, this is the marginal condition, and actually it should be greater than. Okay, while designing it should be greater than this. So I haven't shown the transformer design process in detail. You can check the lecture, and you will see that the process has been explained there in detail. Okay. So now we will proceed to the problem solving part. Okay. And I will take a small break, 5-minute break. And if you have any question, we can discuss that after the break. Otherwise, we will proceed to the problem solving.
Okay, ma'am.
Okay.
Excuse me, ma'am.
Yeah,
Hello.
are you saying something?
Ma'am, can you explain the terms involved in this formula design of transformer?
Uh, can you say a bit louder? I didn't hear.
No, I'm saying, can you please tell me the
Sir, you are
terms
not
that are
audible, sir.
doing it?
Okay, so let's come back after 5 minutes and we shall start the problem solving part. Let's start the problem solving. So, uh, Akshit, you were asking something. Hello? Are you there?
Yes, ma'am, I'm here. I think he not yet come.
Okay, okay. Okay, let's start the problem solving part. So the first problem is an inductor has to be designed with the given specification, frequency 5 kilohertz, relative permeability of the material is 2500, RMS current is 1.5 ampere, number of turns is 25. Calculate the achievable flux density in the core with the given parameters. Okay. So can you tell how we can find out the flux density? So here all these informations are given and also the core dimensions are given. Let's see. So first of all, here the dimensions are given. So you can find out what is the magnetic path length, the mean path length. Okay, you will have to find the mean path length. So that is what. So here this dimension and this all this height, this length, width, all these things are given. So the mean length will be what? The this periphery, right? So this one. So this is 2 times 140 plus 110. This is 140 because this total is 150 and we have to find the mean path length. So that becomes here this is 10 millimeter. So 5 from here and 5 from here will be deducted. So this length is 140. And again this height is 120. So we'll have to deduct 5 here and 5 here. So the mean height this is 110. So and that this total length is, so here basically this is the mean path length where the flux travels, right? So that comes out 500 millimeter. So now we can find out what will be the magnetic field strength H, that is mmf divided by the magnetic path length. So N is given 25, current is given 1.5 ampere and Lm we just calculated. So this is 75. What is mu? Mu is mu r into mu naught. Mu r is given and mu naught we know. So B is mu times H. So this is the flux density, 0.2356 Tesla. Tesla is the unit for flux. Okay, let's see the next problem.
Can you show the problem once, ma'am? The previous slide.
Huh, huh.
Okay, ma'am. Okay, ma'am.
Okay. So this is straightforward. You just need to know the basic principles, the Ampere's law. So here we have used Ampere's law. H equal to Ni by Lm and B is equal to mu H. So this is 0.2356 Tesla. What is the next question? Find the inductance of the coil used in question 1. So all these informations are given, the core dimension along with the switching frequency is given and number of turn is given. So you will have to find out the inductance, right? So here, remember, we earlier we calculated inductance value in the DC-DC converters from the electrical parameters. So there the current ripple specification was given, the input-output values were given. But here we will have to calculate the inductance from the core geometry and the all this information, number of turn, the current, okay. So this information you will have to utilize. So let's see. So we know what is the reluctance of the core. Core reluctance we can find out from this formula, which is Lm by mu Ac. Lm is the magnetic mean path length, mu is the permeability, Ac is the core cross-sectional area. Now Lm and mu we already know. And what will be cross-sectional area, that we will have to find out from this core geometry. So this will be, so if I draw this, this will be the core cross-sectional area, something like this. So this will be the cross-sectional area. Okay. So this portion. What will be this? So this dimension is given 10 millimeter and this dimension is given 15 millimeter. So that comes out 150 millimeters square. And to convert it to meter square, we have multiplied 10 power minus 6. So we can find out the reluctance. And what is inductance? Inductance is n square by reluctance. Or you can also similarly find out. So this is same only. You can also write permeance into n square. So either you will have to find out reluctance or you will have to find out the permeance. Okay. So from this formula, we can find out. So N is already given 25 and reluctance is this. So N square by reluctance is 0.5887 millihenry. That will be your inductance. So the problem you were showing in the starting. So there also, I think the core dimensions were given and some additional information will be given. From there, you will have to find out the L value. Okay.
Okay, ma'am.
Yeah, so you will have to utilize these dimensions, the height, length, width, all this, and you will have to find out either reluctance or permeance, and then n square by reluctance will give you the inductance value.
What about the second equation, ma'am? The one which you have this one. Permeance and n square. This is
This,
also L value, right?
this is n only. So
L.
permeance is 1 by reluctance, right?
Okay.
Permeance that I showed na in the when I was discussing the magnetics part. So permeance is 1 by reluctance.
Okay, ma'am.
Okay. And permeance is this equal to mu A by Lm. This is permeance. And if you just get the reciprocal, you will get the reluctance.
Okay.
So here I want to say that sometimes you will see that reluctance is connected. So there will be some equivalence of magnetic circuit and electrical circuit, and sometimes so flux is basically what MMF by reluctance. So in some literatures they say that reluctance is equivalent to resistance. But this is not entirely true because reluctance is not a like resistance is a dissipative element. There the power is dissipated in terms of heat, but here the case is not like this. So if we have to draw some analogy of electrical circuit and magnetic circuit, so in electrical circuit, what is current? That is the if we want to say current, then the analogy will be drawn to not flux, but the analogy will be with d phi by dt. Okay. So this is the dynamic part. Current is the dynamic part in an electrical circuit. So in magnetic circuit, the equivalent is d phi by dt. And if we talk about voltage, the potential, the analogy is with MMF. Okay. So EMF and MMF, they are the analogy is drawn between them. Electromotive force and magnetomotive force. Okay. So these are the analogies. And power, if you see, power is what? I V into I. And in magnetic field, the power will be MMF into d phi by dt. That is power. Okay. So suppose,
in this problem, while calculating the area,
okay,
like in both the sides, right side and left side, both the sides, you have the same cross-sectional area, correct?
yeah,
Means 10 mm,
right,
10 mm, 10 mm in all the sides.
yeah.
Suppose one side is 5 mm, how to calculate, ma'am? We need to calculate the entire thing, or 10 and 5 we should take. Means to
So
the left side we
so
have
you
10
are,
mm and
so you are saying that this width and this width and this width, they are not
different,
similar.
different, yeah.
Yeah. So usually that is not the case. If you see that, if you see any core, usually they are symmetric. Okay. Otherwise, there will be some difference here. The flux density here and the flux density here, they will be different, right? Because B is equal to phi by A. So here, if A is suppose greater here and A is less here, then B here and B here, they will not be equal,
Okay.
right? And so there may be some problem. So usually this is not the case. Usually if you see any core, so these are symmetric. Okay, there is, if you see toroidal core also, so
Okay.
toroidal core is something like this. So here actually I didn't draw properly, but here the cross section throughout the core will be same. Okay, it is not different.
Okay. Okay.
Uh,
But madam,
because
there
we
is
want to
one.
maintain a uniform B throughout our core. So the B should be maintained uniformly. Okay, that's why. Somebody,
Yeah,
what?
madam, there is a question in the assignment. So there the this width is given as a different.
Okay, so here and here the width they
Uh,
have given differently.
it is a like E core, but the last in the last section, the last leg of the core, uh, the
Actually, it has
width
three
is
limbs,
different.
ma'am. The problem which we are seeing now is having two limbs. The
Huh?
same, the question is same, but it has three limbs.
Yeah.
So in between there is something like this,
Uh,
if I am correct.
yeah,
Yeah.
one more limb is there, and you have already
Huh?
shaded no one portion with red color. That one is
Right.
no. Already you did know that shaded portion for calculating the area.
Okay.
There they have given 5 mm.
Sorry, what? They
So
have given?
left limb is 10 mm, center
Okay.
limb is 10 mm,
Huh?
right limb is 5 mm.
Acha.
That is how they
Okay.
have given.
And what they have asked in the question?
Inductance, L value.
Okay, they
Can
have
I share my screen if you want?
sure. You share.
Yeah.
Just a sec. You share?
You're able to see now?
It is coming. Zoom it a bit.
देखो यहाँ पे 0.5 लिखा है ये, और ये जो है दिस इज 1 सेंटीमीटर, ये 1 सेंटीमीटर है, और ये लास्ट वाला।
So this is 3 centimeter, 3 centimeter. Okay. This is 0.5. This is 1 centimeter.
ना ये वाला नहीं।
Okay. So the point is that here, see, here the winding is across this limb, right?
Yeah.
The winding is in the leftmost limb.
Yes, ma'am.
Correct.
So, right. So I guess I'm not sure, but I think we will have to take the cross-sectional area of although the flux will flow throughout the core, but one solution could be that you will have to find some mean value of the cross-sectional area, or you can take that limb only, like where the winding is there. You can take that limb.
Okay.
But
Thank you,
anyway,
madam.
I will try to, when I will upload this presentation in the drives in the drives one. So one of you can share this problem. I will share that. Okay. I will try to share. I will not share the solution because I think this the due date is not over yet, right? You will have to submit it in some days. So I can't share the exact solution, but for this non-uniform code cross section, that I can share some solution. Okay.
Okay.
Okay. Thank you.
So yeah. Okay. Yeah. So let's take the next problem. So they have asked what will be the input voltage V in question 1. So some input voltage we are giving here. So what will be the value, the RMS value? So here Faraday's law we know E is equal to N dphi by dt. So suppose here actually this is a generalization, okay, but it may not be it, like sometimes the excitation can be of any shape, that I already told you. It doesn't have to be sinusoidal always, but for this particular problem, if we assume sinusoidal excitation here, so then we can also assume that the flux here, this, it will also have a sinusoidal shape. Okay. So phi is, suppose this E is of so the this, if this excitation voltage is cosinusoidal, and if you do d phi by dt, you will get so the flux will be sinusoidal. Okay, you can do that. So if phi is phi m sin omega t, then E, the induced voltage will be, you will have to differentiate it. It will come in phi m omega and then cos omega t, and phi m is Bm times AC, and omega is 2 pi f. And if we want the RMS value for any sinusoidal or cosinusoidal quantity, then it is by root 2. So you know N is given, Bm we calculated, cross-sectional area we know, 2 pi f is given. So from here you can get 19.614. But here the approximation is that we are assuming a sinusoidal excitation. Okay. But remember, for DC-DC converters, it is not actually, most of the cases it will not be sinusoidal. it will be some square voltage or some quasi square, something like this, not not a sinusoidal excitation. Okay. So yeah. What is the next question? If the required inductance value with the same core size is 20 millihenry, then calculate the number of turns to be used for the inductor design. So what they are asking that now our required inductance value is 20 millihenry instead of that we calculated some 0.588 millihenry. So what will be the number of turns? So earlier it was 25. Now what will be the number of turns? So it is very easy. So the same relation we can use. So basically L value, we know what is L1, what is L2. We also, so they have said that we can use the same core. As long as the core is same, the reluctance will be same, because reluctance is dependent on the core dimension and the core permeability. As we are not changing the core, so reluctance will be same for both the cases. So the number of turns we can calculate here. It will be 146. We will have to round it to an integer. So it is 146. Okay. So this is so which of the following statement is true? So yeah. So you can tell me from these four options which are correct.
First one is true, ma'am.
First one is true.
Yeah.
Others?
मुझे लास्ट लग रहा है डी नंबर का।
So correct options are option D and option C.
Oh.
Okay.
What a current
So
flow.
basically, see here, saturation is a magnetic phenomena. So you can't really say what will be the resistance. Resistance is a electrical circuit quantity parameter.
Okay.
So for magnetic circuit, the resistance, high resistance doesn't make sense. Okay. So during the saturation of the magnetic component offer high inductance. No, actually the inductance value reduces during saturation. Why? Because so L is permeance into N square. And permeance is, we already saw what is permeance, or you can also express in terms of reluctance, same only. So this is mu A by L. So cross-sectional area and magnetic path length times N square. Right. And during saturation, what we saw, if we see the BH curve, so during saturation, basically the slope reduces. So if the slope reduces, that means that mu also mu reduces, right? Because B is mu H. So if mu reduces, then obviously your inductance value will also reduce. So during saturation, inductance value is not high, it becomes low. High amount of current will flow due to saturation of magnetic component. Yes, this is true. If the magnetic component is saturated, it will draw huge current. And option D, constant DC voltage is applied for long duration, that will lead to saturation. Yeah, because if you don't maintain volt second, suppose you are giving this kind of a voltage across an inductor or across the winding of the transformer, then obviously it will lead to saturation, because here the volt second is not maintained. For volt second in a cycle, for some duration you will have to positive, and for some duration it will have to be negative, so that the average of this is zero. The average voltage has to be zero. If there is an average voltage like this, then it will definitely get saturated. Okay. So C and D, these two options are correct. Yeah. So now here is one question. So this is a boost converter with input voltage of 20 volt and a duty ratio of 0.4, delivering a power of 100 watt. Calculate the value of inductor. You and if they have given delta IL is 10% of IL, that means that your current triple is 10% of average inductor current. Switching frequency is given, and assume a lossless circuit and continuous conduction mode. The required permeance is this. Permeance value is given. Okay, and relative permeability is also given 2000, and some code list is given. From there we will have to select. Okay, so we will have to design this inductor also. So first of all we need the inductance value, so that we already know how to do that. Output voltage for boost converter is V in by 1 minus D, 33.33 volt. Average output current, so output power was given, output voltage we calculated, so output current will be this. And average inductor current, so for a boost converter, the average inductor current is I naught by 1 minus D. For boost converter, if this is your inductor current in continuous conduction mode, then the capacitor, so during this portion when the switch is on, the capacitor provides the output current, and during this portion the inductor current is equal to this output current. So average in inductor current is I naught by 1 minus D, because this duration is 1 minus D. Okay, so this duration is 1 minus D. So you can also find this relation out from the power balance equation. So input power is equal to output power for a lossless circuit. Here the input current is nothing but the inductor current, because the inductor is in series with the source. So V in into IL that is equal to V out I out from power balance. Okay, from power balance. So IL is what? IL is V out by V in into I out. V out by V in into, sorry, into I out. And V out by V in we know that is 1 minus D. So IL would be I naught by 1 minus D, that is 5 ampere. And peak to peak ripple is 10% of average inductor current, so 0.5 ampere. Now if you see this equation, so during when the switch is on, V in comes across the inductor, so V in D by del IL Fs. We already discussed this numerical in the when we were discussing buck converter boost converter in that tutorial session. So from this we can find out the L value 0.533 millihenry. Okay. So now we have the inductance value. Now we can proceed to the design part. Okay. We can proceed to the design part and we will design in the same way that we discussed, step by step. So first, we will find out what is the maximum current through the inductor. What it will be the maximum current? So inductor current is like this, right? So there is average value and there is some ripple. So this is the maximum current, maximum inductor current, and that is what that current is average plus del IL by 2, where del IL is the peak to peak ripple. This is 5.25 ampere. IL we already found out 5 ampere and del IL value is 0.5. So this is 5.25 ampere. So the maximum energy stored in the inductor is half L I max square. So this is 7.34 millijoule. Now we can find out the area product. So to find some code from data sheet, we need the area product, right? So area product formula is this, where this is the window utilization factor, this is the crest factor, this is the current density, and this is the flux density, right? This formula we saw in the beginning. Crest factor is what? Crest factor is basically I max by I RMS. Okay. I max by I RMS. I max we found out and I RMS here is same as the I average. So that would be 5 I RMS. So that is 1.05. Okay. Window utilization factor, you can take any value 0.4 to 0.6. So this is 0.6 we have taken. Peak flux density is for ferrite core. It is restricted to 0.25 Tesla. So 0.25 Tesla. Current density is this. And so we can find out the area product from that formula, which comes out to be this from this formula. Okay. So from this chart, if you see, only this code satisfies this. So only its area product is 47,784. Otherwise, all these are lesser than this value. So we have taken this code. This is a port code. So 42 by 29. So this code we can use. Okay. And what will be the required conductor cross section area? That will be IRMS by J. So this will be the required conductor cross sectional area. Now we need to find out permeance. And we also need some air gap, right? Because we told that we will need some air gap for inductor to reduce the slope. To reduce the slope, we need to find out the air gap. So we will introduce some air gap. And so what will be the air gap length? So permeance value here it is given in the question. Permeance is already given. Permeance is given. Mu naught you know. Mu r is already given. AC you can find out from this chart. Cross sectional area is given 264 millimeter square. LM is also given here. Sorry. LM is given. Mean magnetic length it is 68.6 millimeter. So all these values we know. The only unknown is LG, which is the air gap length. So that comes out to be 0.6 millimeter. Okay. So this much air gap you need to provide for your inductor. And then N, what will be the number of turns? Number of turns is root over L by permeance. This is 32. Okay. So now you have calculated all the required parameters, the number of turns. Okay. And now the only remaining thing is that you need to satisfy this criteria. You need to see whether the where you have selected that is that you can accommodate in the window. Okay. So we already calculated the required cross section area, which is 1.67 millimeter square. And from this is the chart which I was telling you. So this is the wear chart, okay, where the diameter of the wear is given. You can see this SWG1. So I have not shown this, but you can do it by yourself. So this SWG14, this satisfies this criteria. KWAW greater than AN. So this is N, this is A, and N you have calculated 32. Yeah. So the point is that even if you choose this SWG13, then also you will see that cross sectional area comes out to be greater than this. But SWG13 doesn't satisfy this condition. So there you will find AN is greater than KWAW. So that's why you will have to check 3-4 wares and you will have to see which one satisfies this equation. Okay. So this where you will need. And here there is another question. So which of the following is true? So this is very basic. Inductor. So inductor is an storage element and transformer is a energy transfer device, right? So these two are correct, A and D.
Ma'am, what is KFE, ma'am? KFE means what?
Where is KFE?
KFE. No, not in the slides. I'm just asking. Like you have given here KW, na? Like that, KFE is there. What it could be?
KFE.
FE.
Okay, so like this, K and in the suffix there is FE.
FE. Yeah. F and E.
Okay.
Yes, yes. What it could be?
Mm, I am not familiar with this term actually.
Okay, ma'am.
KFE, I don't know.
Okay.
Okay, I
Proceed.
will have to check. So
Okay.
have they given any value? What is value of KFE? Have they given any value?
No, ma'am, they have not given any value. We need to find out the KFE value. KFE value. It is coming in power loss density formula.
Power loss density.
Power loss density is equal to KFE into B max power beta.
Okay,
B
but I
max
think in the lecture all these things are not discussed. Where they are giving all these questions?
in the
In the
assignment.
lecture all they are not
The,
covered actually.
no.
Okay, so do one thing.
Yeah,
Whatever doubt you have, like all these terms and the previous question that you were saying with
yeah.
non-uniform cross-sectional area, you list it down and you send it. Okay.
How do I send, ma'am? Can
Okay.
you
So
share your mail ID?
yeah. Okay. I will share my mail ID. So I
Okay.
am writing it here only right now.
Okay,
You
ma'am.
note it down.
Yeah.
And you can send me. I will try to answer. Okay.
Okay, ma'am.
Yeah. Okay.
Ma'am, move the cursor, ma'am.
Sorry. I have sent it in the chat section.
Okay, ma'am. Thank you.
Okay.
Not coming.
Okay.
No, it is not coming. Means chat is disabled, it seems.
Chat is disabled. Acha. Okay.
I will.
Oh, okay. Now can you see it?
Yeah. 1 minute, ma'am.
You see, it shouldn't be. I think you should. You should be able to see it. I don't know. It is not disabled.
ये visible है मैडम, वो सिर्फ चार्ट नहीं आ रहा है, but anyway we can
Yeah. It
just
is
note
visible
down.
only, ma'am. I note it down. Not a problem.
Thanks, thank you.
Okay, okay. Okay, you send in this mail ID.
Yes, ma'am. Sir, are you able to solve all the problems, sir? Sir?
Hey, what was the question? Yeah.
No, I'm asking. Total 10 questions are there. I'm unable to solve 4 questions, 5 questions actually.
No,
Little difficult.
yeah, we'll discuss later. Let us this session
Yeah.
go through. Yeah.
Okay. Yeah. Thank you.
So,
Yes, ma'am.
so this is the this will be the last question, I think, today. So yeah. So there are the specifications for two coils are given. For coil one, so both are ferrite cores. So this is the mu r is given. Mu r, then magnetic path length, then air gap length, and the number of turns current. And the same parameters are given for coil 2, right? So they are asking that so mu naught value is the standard value that we usually use. What will be the flux through coil 1? If the flux through coil 1 is phi 1 and flux through coil is phi 2, then you will have to find, I think I haven't written the question. So you will have to find out the ratio of phi 1 and phi 2. You will have to find out the ratio. Okay. So can you say can you tell how to find out this? How to proceed? Like what will be the step? This is very easy question actually. So do you can you tell how to proceed? This is very easy. So what is phi? What is flux in any core? So flux is mmf by reluctance. So mmf you can find out readily. So n is given, I is given. So ni is already there. And reluctance you can find out from the core geometry. So this is reluctance is Lm by mu A. So from here you can find out reluctance and then you can find out phi. Okay. So can you tell me, like, can you calculate what will be phi 1? What will be phi 1? Calculate and tell me. So mind you will have to convert all the dimensions in meter in the SI units. So these dimensions are given in millimeter, but while calculating, So LM and A you will have to convert to meter or meter square. So I have not written this. You just calculate and tell me what will be phi 1 value and what will be phi 2 value. Hello, are you there?
Yeah, ma'am, I'm trying, ma'am.
Okay, okay, do. Okay. So your mu will be mu or mu naught.
R value is 13 in 10 power minus 10 power 6. 13 milli, sorry, 13 mega is coming. Reluctance value.
Okay, you just tell me phi 1 value. So you do Ni by R and you
Yeah,
tell me what is phi 1.
7.6. 7.6
Okay,
micro.
okay, I don't have calculator with me right now, so
Yeah,
I
yeah,
won't
even
be able to verify. But
I'm also not having,
5-1,
ma'am. Yeah, 5.1 is 7.69 into
okay,
10
and 5-2,
power 7.69 into 5.1 I'm
7
telling.
points.
No, 5.1 I'm telling. 7.62 in 10 power minus 6.
Okay, so
5.
7.62 micro.
Yeah, micro. And 5.2 I should check. So I don't have calculator. That's the problem, ma'am. I'm using mobile only.
Okay, okay.
5.2 similarly we should calculate. LM2.
Let's verify.
We will do it, madam. I think no problem. For me also, I don't have a calculator. But we have understood now. It is everything is given, formula is given, so it is just putting the values. So we
Okay,
can.
Yes,
okay,
ma'am. We will
fine then.
proceed then.
Okay, okay, fine. You do it. And then you send those problems, mail me, and I will in the drives folder where I upload the presentations, there only I will upload the solutions.
Okay, sure.
Ma'am, will you upload by tomorrow?
Uh, I will try, but I have some other work, so I will try within tomorrow. But yeah, tomorrow or day after tomorrow, I will try.
Okay.
So what is
Okay.
the deadline for this
Day after tomorrow, ma'am.
submission? Day after tomorrow. Okay, okay, I will see. Okay.
Okay, ma'am.
You
Thank you.
mail me today only. Okay.
Okay.
Okay. Okay. Thank you for joining. Then we can
Yes.
conclude today's session.
Thank you.
Yeah.
Thank you.
Thanks. Thank you.